What I have done in this space and what I'm thinking about this topic, and what's my opinion in general. Before that, like a quick introduction about me and my lab. So I'm Constantinos, I'm from Greece, I have an electrical engineering background. I did my PhD at Rice with Professor Lydia Kavraki, and now I'm at WPI in the Robotics Engineering Department. For those who don't know, WPI has a pure robotics department. We have a lot of professors there, so hopefully we'll have some super exciting things to show what the department can do in robotics in the future. So at WPI, I'm working in the intersection between learning and planning. I'm leading the efficient learning and planning for intelligent systems group. We have 3 research areas that we focus that we think are important. One is how can we use learning to improve paralleling efficiency, how we can use learning to plan direct from images, and how we can learn models of the world that allows to plan in challenging manipulation scenarios. So, inspired from one of the talks yesterday that said this is my talk, so I'll talk a little bit about my work, and then I'll talk about the benchmarking things. Some of the things we have done. Last year we published our first paper where we can, it's on the efficient motion planning, and you can create a mapping from the task space to the configuration space, and you can guarantee that you can generate continuous and smooth paths from any task space to the configuration space. You can show that that's possible in certain cases, so it has a lot of applications to teleoperation. Some follow-up work. We have another topic, how you can solve kinodynamic problems with spatial temporal logic constraints. So the main idea is we used SST under the hood, and we figured out how to incorporate the cost to make sure we can satisfy all these constraints. How we can plan directly from images. I'm sorry, I don't know how close I should speak or not to the microphone. Can you hear me from here? Yeah, okay, cool. How we can plan from visual spaces directly. We can do planning in the observation space without having access to the configuration space of the robot. And the final work that we're more excited about is on non-prehensile manipulation. Ali, my student, worked on this. He's here, where you can use a planner with a learned non-prehensile model, and you can figure out how to pick up an object by pushing at the edge of the table without explicitly telling the robot that it has to do that. So this is about our research, and now I'll go into the main talk. But happy to talk about this as well. So today I'm going to talk about 3 things for motion planning. One is OMPL, Planner Arena, and Motion Benchmaker. This answers the 3 questions: where are all the planners, how I can benchmark them, and what problems I can test them on. So the first thing, before I even talk about OMPL, I just want to really quickly to mention what we mean by motion planning, because I think everybody maybe view the problem differently, so I just want to make sure we're all on the same page. There are many extensions of the motion planning problem. So here, in a nutshell, what we mean by motion planning, we're talking about the geometric motion planning problem, and we're given a start configuration of the robot, a workspace obstacles that we're trying to avoid, a goal configuration of the robot, and we're trying to find a path from start to goal that avoids the workspace obstacles and respects the constraints of the robot. So this is the problem we're trying to solve, and it's a general problem, but here we're going to see it in the context of manipulation. Now, to make it a little bit more formal, just to make sure we're exactly on the same page, we assume that the quasi-static assumption holds. So this means that in order to describe the state of the robot, the only thing I need to know is the values of its joints or its position, and that any curve in the configuration space that's collision-free can be followed by a controller. So we don't, for the geometric motion planning problem, we don't have extra dynamical constraints. So formally, we have X, which is the configuration space of the robot, which fully describes the position of its body. We have implicitly defined configuration space obstacles, which are regions in the configuration that we cannot, they will violate our allocation, will violate our constraints by colliding with it, which also defines, by taking the complement, the collision-free space. And we're given a start, a goal, and we're trying to find a curve that goes from the start to the goal that's collision-free. So that's the problem we are benchmarking. It's the simplest motion planning problem with the fewest, with the most assumptions, I would say. So yes, and this, as we said, we're going to do it for manipulation. We're interested in high-dimensional problems and what kind of planners we want to use in these situations. Like the Baxter, the FETs, you can also use these techniques to plan for even the Robonaut in the International Space Station. It's going to move. This is, yeah, I should have quoted this is Zach Kingston's animation, the other two are mine. But yeah, that he made this nice figure. Okay. There are different types of motion planners. This is just one categorization. Now there are many hybrid methods that take ideas from both. For example, sense-based algorithms like A-star, weighted A-star, trajectory optimization algorithms like Trajop, Chom, graph of convex sets. That's kind of a hybrid method that I put it here, but also Gaussian. Oh, sorry, I forgot that Gaussian process. It's Gaussian process motion planner, something like that. And sampling-based planners like PRM and RRT. The first thing, I want to say where we can find all these planners, or if we want to benchmark them. So besides the amazing collection that Adam and the team Compartim has put together, most of these planners, unfortunately, you would have to find them on the original implementations and papers of the people that have written them. But specifically for sampling-based planners, there was a big effort by my previous advisor lab at Rice University to create OMPL and put all the sampling-based planners there. So OMPL was published in 2012. It's an open source library that has many open source implementations of planners that are usually being contributed by the authors themselves. So the people do not, that lab doesn't go and code all the planners themselves. Sometimes they do, but also the authors of the papers, they go and they contribute the papers there directly. So what's OMPL? Real quickly, it's maintained by my previous advisor, by Lydia Kavraki at Rice University. It's a C++ library. It has Python bindings. You can do pip install OMPL. I can help you do that if you need. They try to make it really easy to use. It has core assumptions, how to represent the configuration space, how to do the sampling, all the things you need to take care of if you want to create a new planner and you want to have a standard interface. And it can be used for, it's being used for research, education, and industry as well. And of course, they had to take some, they had to take some things out of the complexity. So the thing that OMPL does not have, let me say it here, is that it does not, it's an abstract interface of planners, so it doesn't have specific robots and workspaces. That thing is abstract away, so you can plug and play it in different applications. So that's something you have to provide yourself. Nonetheless, it is very helpful because it has all the planners, standard implementations, and with minimum engineering, you can apply it to your problem. And these are some of the planners that are there. This is from 2022, but there are more newer planners. The geometric motion planning problem is the single query planners and the optimizing planners. They can find the optimal path asymptotically, but there are also some extensions to the geometric motion planning problem that those planners address, like constraint-based motion planning, dynamic planning, learning-based motion planning. That's, again, the geometric motion planning problem. Sorry, you want to take a picture? Yes, so these are the planners that are available on OMPL that have been implemented, and these are all the different papers. I think we have one of the authors here, and I'm pretty sure Kostas has many papers here too. Can't find your name, but maybe because you were second author or last author, Okay. Yes. So moving on, So this OMPL. So now OMPL, as I said, has all these planners, right? Many different planners. Everybody claims this is the best planner that they should use, and they have demonstrated that clearly in their paper, right? But you have your new application. You want to figure out which planner to use and how to benchmark it. So again, so what you are going to do, you're going to need two things. First, you're going to need a set of problems to check the performance of your planner. So you need a sequence of a set of motion planning problems. And the second is you also need some benchmarking capabilities, maybe some visualization, some metrics, some logging capabilities, etc. So both those things were also provided with the original OMPL. It had this, it was back in 2015. These problems are relatively toys, but they were still complicated in terms of difficulty because you had to go through narrow passages, etc. So they're still available. Sometimes, I don't know, I think nobody uses them yet, but they have been used a lot for motion planning research, and people have been benchmarking them to show their planners. But these are like up to 6 degrees of freedom, free flying robots, etc. They are not real robots. But these were provided with the original, not with the original OMPL, but as an extension to OMPL, it was called OMPL app. So there's implementation, and the other thing that also was provided was benchmarking capabilities for visualization and proposed metrics. One thing that's important with sample-based planners is because the performance is very stochastic. You shouldn't just run them once per problem. You should run them multiple times and see what's the performance. That's why when you're doing research in sampling-based motion planners, we always provide box plots over hundreds of iterations on the same problem, because the performance can be very different. And we don't just look at the median, we also want the variance, for example, to be small. So this is also another tool that was provided with OMPL. Later it was developed, I think it was at this paper, on how you can actually benchmark the motion planning problems, and that was the problems that were provided. And this is an available web interface, again maintained by my previous lab, where you can actually run different planners in OMPL. You can log down all the results, and you can plot them into Planner Arena and see different benchmarks. It's very interactive. You can also go, for example, can you see my mouse? Yes. For example, here it says benchmark attribute. They had a bunch of different metrics that are automatically logged, and you can plot them and see, based on the metrics that you care, which one is best. Yeah, and these were really good software engineering people, so they've done a great job. You can extend this, it's modular, etc. And this was worked by Mark Moll, who was also at my lab at that time. All right, so yeah, this is what was provided before 2003, and this definitely helped drive a lot of the research in motion planning, especially the geometric motion planning problem. However, nowadays, we have real robots. We care about manipulation. I don't know if my free-flying piano is going to be a good benchmark for my pick-and-place task, right? So I actually would like to have some more realistic environments, like this one, where I might still be doing the geometric motion planning problem, but I know that that's part of my end-to-end manipulation problem, so I need to be able to solve that one efficiently, which is very different from those benchmarks. So now that we have this robot, we have some ideas of the problems I want to solve. We needed these benchmarks, and I was surprised that when I was starting my PhD when I started my PhD, my topic was as I said, in the intersection of machine learning and motion planning, so I also needed a lot of data to train my algorithm, right? So I was surprised to find that there were no existing data sets, or a very simple, or not simple, very few data sets, maybe 5, 10 motion planning problems that were used sometimes to show that, yes, my planner is better in these 10 problems than the other planner. So the question, yeah, how will my planner perform on a real robot, on a real manipulation problem? Many times what happens is, yeah, people would just choose a few problems, which might make sense in some cases, but in others it might not, right? You might show that in this case it's better, but you definitely don't know in general what's happening, and you also don't know, you can't also learn with this, like you need a little bit more data. All right, so I already said a little bit the motivation why we needed larger data sets for motion planning. One more thing I wanted to say was, because the performance of these motion planners is very stochastic, not only do you need to check how, you have to run them multiple times per problem, but even in the same class of problems, and when I say class of problems, let's say you want to pick up an object from this shelf, but this shelf can be in different locations, and the object needs to be in different, also in different locations. Even within the same class of problems, their performance can vary greatly. So for example, if you had, let's say you have two planners, and you want to see which one is better, the yellow planner or the green planner. And these are real planners. I didn't make the results up. They are real results, but we don't care about the details of the planner. So I want to say which one of these planners is better in terms of planning time. If I just use 5 motion planning problems, even if I run it multiple times, I will have a lot of, even if I run it multiple times, the conclusion that I might arrive to, for example, here the yellow planner is better, might not be correct. Because if I add more problems from the same class of problems, then you can see here that the green planner is actually better. Okay? So having a large data sets of motion planning problems like start, goal, and workspace tuples is really important to be able to derive the correct conclusion and benchmark and get the correct comparison between these planners, at least in this class of problems. And the other thing, as I already said, is that we needed large data sets for learning-based planners, and as I said, they were not openly available data sets. So what we did, basically I was creating my own data set, and after many years that I saw that there are still aren't many data sets, I found some other researchers from other universities, from TU Berlin and University of Wisconsin-Madison, and we put together also, they were doing motion planning, we put together all our motion planning problems, and we created a data set that was both a data set of motion planning problems, but was also a generator of motion planning problems. So you could specify a distribution of problems and you could sample from them. And that was called Motion Benchmaker. Really quickly, how it works, I don't have a lot of time. It's a modular framework, so you can mix and match these different things. It has a scene sampler that basically samples different locations of obstacles. You can define how to do that. Then you have the problem generator that takes as input the objects, the robot, and some affordances, and does inverse kinematics, which is also robot agnostic. So you can take any scene, you put and any robot you put in the problem generator, and you get a full motion planning problem out. And also the Octomap generator that can convert your geometric scenes into occupancy grids from a point of view from a camera. So it's like more realistic if you want to apply this in the real world. So yeah, really quickly, how this look like. For example, you can sample different locations of the obstacles. You have to define exactly how the sampling will happen. And we also had URDF sampling. That was a very cool idea, realized, but you can represent your object as a URDF, and then you just sample in the configuration space of the object, which is like your object is a robot essentially, and you just sample different locations of the robot. So that's how you create different scenes. Then you can put these different scenes with some affordances inside the problem generator. And then you do inverse kinematics, you find the start and the goal, and then you check if this problem is feasible by actually running the motion planner, because you might create an infeasible problem, and if it's feasible, you can store it in your data set. And that's how you can sample feasible problems. And in the end, as we said, we also have the Octomap generator that was converting the geometric scenes into occupancy grids. And you can easily generate, as I said, different motion planning problems. You can sample start and goal locations, locations of the obstacles, etc. So as I said, it's a generator. And the other thing you could do is, as I said, you could use the same scene. We try to make the problems robot agnostic, and it will automatically figure out how to do different robots in the same scene. So you create different motion planning problems. Of course, this can be vastly more difficult. For example, the Franca, which is interesting, right? So the Franca problems are all easier because the Franca robot cannot go inside narrow passages, so it cannot solve harder problems just because of its kinematics, right? So in terms of motion planning problems, all the Franca problems are easy. But the FETs, because it has a weird, it can go really deep inside the self, you can actually create extremely hard motion planning problems. It has a wide range of problems it can solve. And for example, as you increase the degrees of freedom, it gets harder and harder as well. So that's also something that you have to take into account when you're solving a motion planning problem. And besides the dataset generator, we also used it to create comprehensive sets of problems. So we had like 5 robots and across 8 scenes, and we created 100 different motion plannings for each one. So this actually became a dataset as well that could be used as a standard benchmarking tool for benchmarking set for different motion planners. And we did this, and the motivation was, yes, to also help the community, but also out of frustration because we would compare with something, they would tell us, oh, this is not a valid comparison, or we would see other papers being published in the same topic, but they would make their own benchmarks, and we wouldn't consider fair. But of course, everybody has their own metrics, but I said, okay, let's create this, and it's fair game afterwards. So yeah, I won't claim this is what AIMAGNET or anything, but at least it was used by some people. I was really happy when there was the first workshop this week that on parallel motion planning, that many of the papers there actually was building on top of Motion Benchmaker. So for example, the Kurobo, the VAMP papers, those that recent papers have been parallelization motion planning, they are all benchmarking in these environments. And people were also able to use them in other cases, for example, add new robots, for example, the Kinova arm, or also use the Octomap generator to study the occupancy of the free space properties of motion planning problems. So I was really happy to find out that it had helped people and it found some adoption. And the final thing I want to mention is afterwards, because we saw that many people had created their own benchmarks, they just didn't see the value of publishing them or they didn't have the incentives to do them. We made a workshop which is on this topic, and we said if you have benchmarks or something you want to share with the community, please submit them, and we're going to host them on this website afterwards. So many people submitted their benchmarks as workshop papers, and we have a list of everything that was submitted there with the data sets, the codes, everything that they want to give us. And there are many data sets there for motion planning in general, not just manipulation, but overall motion planning problems. So the final things, maybe I'm preaching the choir here. I think the first, I said doing evaluation is difficult. Definitely if you're working on a challenging motion planning problem or manipulation problem and you have created some data sets just because you had to, you couldn't find them, I would definitely make the effort to publish them and share them. I think it's both a rewarding experience and you're helping the community, and you can also make sure to add it to the organizers' effort. So that concludes the end of my talk. Just a recap. I just talked about some evaluation on motion planning, including OMPL, which includes many sampling-based planners, Planner Arena that allows you to visualize and compare different metrics, and Motion Benchmaker, which is a modern framework to both generate data sets, but also a data set by itself. That's it. Thank you very much.
Questions?
Yes.
So this is great infrastructure that focuses on one module, and we talked about modularity, and it's great. But then let me take the point of view of the system now, right? How can this infrastructure also support things where you will do the integration with perception and other modules, and perhaps you're still evaluating the planners?
I think being able to do the full end-to-end pipeline evaluation is really important. I don't think this I can on myself extend it to be like a full manipulation pipeline, and I don't want to make it either. I think I can make it just about evaluating the motion planner. The only thing that I think makes sense is if you can also have some flexibility in terms of the inputs and the outputs that you produce, so you can make it more, you can test different properties of the motion planner. But I think it needs to be a really big community effort to have tools that test end-to-end performance. And I don't know if you would have to structure it like this.
I think the biggest bottleneck could be actually scene representation, right? And how this would be communicated between.
Okay. I think the scene representation actually, I don't think if it would be such a huge. Okay, that might be a hot take, but for motion planning, I think you can create really interesting problems with very simple primitives, right? And it doesn't matter. For example, you can just have boxes, and you can create full scenes. So you can represent the boxes extremely simple. And this is how this is actually being represented. It's just a sequence of primitives that are being stored in a YAML file. And then you can import it into any simulator that you want. But that's for motion planning, right? If you want to have interactivity, pick them up, do an actual manipulation task, it wouldn't work. But if you want to do end-to-end task performance, that wouldn't work. But for motion planning, I don't think the details, the corners of the object matter, if that makes sense.
I'd love to see a motion benchmaker that is, grasp benchmaker. But then we already had our discussion about contact representation and how that's
it's going to be different, I think.
So like riff on that idea, what if you to expand it onto manipulation, what if you had like a common set of like easily available objects, and maybe there are even 3D printable objects, and instead of motion problem generator, you have a manipulation problem generator. If you could get into very complex scenarios, I think with just like a half dozen objects.
No, I think that's a great idea. I think NVIDIA tried to do something like that. I think it's called Cabinet something. Yeah, I think that's a great idea. It just needs someone to do it. That's it. Or like popularize it a little bit more.
So yeah, I think this is a thing we should pull at, thread we should pull at during the breakout. It's
Okay, cool.
in about an hour. But yeah, that's because I think there's a lot there. Awesome. Thank you very much.